Hello.
It's me.
Hey, what's up guys? Today, we're going to be implementing a simple, novel, data-driven, state-of-the-art machine learning architecture as an atoll, which is what you're gonna be if you don't keep up. But before we get started, don't forget to smash that subscribe button. If you've already subscribed, make another account and subscribe again. We're trying to hit 1 million subs by Christmas, folks. Can we make it? Well, that's up to you. Today, we're going to be using machine learning to predict the denary level of protein structure. Yes, you heard me correctly. Not denatured, but denary, as in the 10th level of protein structure. Now, for those of you who actually paid attention during AP Biology, you may be wondering, but aren't there only 4 levels of protein structure? There isn't such a thing as the denary level. Well, I'm here to tell you that with machine learning, anything is possible. Here at DeepMeganMind, we believe that AI could be one of humanity's most edgy inventions. Machine learning, machine learning, machine learning. We have achieved state-of-the-art results, but we will not be releasing our data or training code unless you're the winner of Squid Game. In that case, you can have your data and training code, and we'll pay for your first 10 sessions of therapy. Now you may now be wondering, why? Why do we need to understand the 10th level of complexity of a protein? What is the impact of our work? Well, imagine a world in which we did. There would be world peace, coronavirus would be solved, and Sublime Text would stop asking me to purchase a license after my free trial expired. Alright, let's get into it. First up, data. As you can probably imagine, we don't have very many denary level protein structures. So after searching far and wide across both public and proprietary databases, we constructed a dataset of size 6. We made sure to clean our data because, well, you know, it got a little bit of Rona on it, which is further split into a training set size of 3, validation set size of 2, and a test set size of 1. We're going all or nothing here, folks. We're gonna black box the shit out of these 3 training points. Our machine learning architectures are called the Jedi, Megan Amber, Revolutionary, Chipotle, Egg McMuffin, Go Bears, Renegade, Jeff Bezos, Net. Our architectures are multitask with a little bit of single task on the side. Which activation function do we use? ALU? RAYLU? Leaky RAYLU? Drippy RAYLU? Sigmoid? Megtan? Well, the answer is one of each. Okay, so let's now get into how these ML architectures actually work. We're going to start out with an input sequence, which is then passed into MSA embedding, which is then passed into a 10D convolutional layer and a pooling layer, which is now fed into a fully connected layer. And then next we're going to pass that into a Rubik's Cube, but not the ordinary 3x3 Rubik's Cube, but the megaminx cube, because we're edgy like that. And then we were feeling a little dangerous, so then we pass it into another fully connected layer. And then now we're going to do the Renegade, which is then going to now play around a red light, green light, which is then fed into the output layer. By the way, did I mention? These architectures are simple, and all hyperparameters were optimized via expertise. Now you might now be wondering, which ML library do we use? Was it PyTorch? Was it Keras? Was it TensorFlow? Well, the answer is all of them. Just make sure when you import torque and type in torque.cuda.is_available open parentheses close parentheses, it returns true. Now let's move on to training, shall we? Our models were trained using mini batch gradient descent with the atom optimizer of batch size somewhere between 1 and, well, 3, for an average between 10 and 1 million epochs. Weights were initialized with Xavier initialization because, well, Andrew said so. We used a learning rate of 0.000000001 that was decayed with the plateau scheduler and deployed dropout probability somewhere between 0 and 1. Okay, so what metrics do we use when evaluating our models to obtain state-of-the-art results? By the way, did I mention that we're state-of-the-art? Well, just in case you forgot. We're state-of-the-art. We use the Pearson R-squared of the MAE, of the MSE, of the area under the curve, of the RMSE. Between ground truth and prediction. Alright, so let's now visualize our results, which are, well, you know. Let me just...
Shift Enter.
Us, everyone else.